Hello everyone, we're going to start lesson 4.3 today, the derivative of a quotient of two functions. We just finished the last lesson on 4-2, the derivative of a product of two functions, and we learned a new formula for that, because you can't simply take the derivative of the product is the product of the derivatives. The quotient rule will follow very similar in that manner. As we go forward, you'll start seeing the new formulas and what we have to do, and there's quite a bit of algebra manipulation that we're going to work with today to help move us forward in our future topics as well. All right, for this first slide, it's our warm-up for today. I do encourage you to pause the video and try to find g prime of x for number 1, and then for number 2, write the equation of the tangent line of f at x equals 3. All right, the two answers for these, the first one for number 1, I just read it over on the left-hand side, d dx of b to the x, or an exponential function. So for example, 5 to the x equals 5 to the x times the natural log of 5. So g prime of x is going to have the chain rule involved with it. So we're going to get the derivative of the outside function with respect to the inside function will be 3 raised to the 4x squared plus 1 times the natural log of 3, that's the ln of the base b, times the derivative of the inside function, which will be 8x. So that's our answer to number 1. Number 2, we have the tangent line. So the tangent line equation y minus y1 equals the slope x minus x1. And for that one, we needed to use the chart. So the chart's a little bit small with that, but we needed a point of tangency, okay, which will be 3, 1. Okay, those are coming from at this. When we go over to 3, we get 1 out. And then we need the slope, and the slope is going to be f prime at at 3. So f prime at 3 gives us a slope of 2. So there's not actually calculations that are required here. It's understanding where the slope comes from and the point of tangency being part of the tangent line equation. And we get y minus 1 equals the slope 2, x minus 3. One of the other ones we were asked on our test, and I don't have that one ready to go for this one, but it was a composition of functions. So this question number 2 was very similar to a test question we had that we're trying to work out some of the kinks, and we could be asked to find composition of functions as well, but we're going to hold off on that part of that today. All right, so lesson 4.3, like I said, is the derivative of the quotient of two functions. We have several examples that really hammer home algebraic examples, and then we have examples that help with tabular data as well. So here's our first exploration. This is not on the guided notes, but just showing you how this kind of works out and how we kind of get to the quotient rule. So x to the 8th divided by x to the 4th does reduce down with power rules of x to the 4th. We know that that derivative is 4x to the 3rd. So if we were to try to differentiate the numerator and denominator separately, would we get 4x to the 3rd as the same derivative? So let's try that out. So d dx of x to the 8th is the derivative of that is 8x to the 7th. And then d dx of x to the 4th is 4x to the 3rd. Well, if we put those into the derivative, into a quotient and clean them up, we end up with 2x to the 4th, which does not match the derivative of 4x to the 3rd. So the quotient rule is not simply the derivative of the quotients. Okay, it's a little more complicated than that. So clearly not equivalent, we have to work with that. So it actually, the derivative of the quotient involves the difference of two products. So here's our formula that we're going to be working with today, the quotient rule. So I recommend writing this down, putting it on a big idea sheet, writing it out on a flashcard, note card. It's going to be something that's really important. So y prime is going to equal the derivative of the top function, okay, which is u, the top function. And you'll hear me refer to it top and bottom. You are welcome to say numerator and denominator as well. We're just trying to clean it up to make it a little quicker to say. So u prime times v minus, instead of plus, u times v prime, all divided by v squared. So the product rule looks just like the numerator, u prime v, but it's a plus sign, and then u times v prime. So the quotient is going to have division and subtraction. So order of operations do matter, which with the numerator and the denominator, which one is the top and which one is the bottom function. So for our quick exploration, we have two functions being divided, and we know that they reduce down to x to the 4th, which has a derivative of 4x to the 3rd. So if we apply this derivative, new quotient rule, this is what it's going to look like. G prime of x equals the derivative of u times v. So this is my u function, u prime. This is v, this is u, and this is v prime. Okay, all divided by v squared. And so just kind of showing on this example that we can put those pieces into the quotient rule. And then we can clean up the numerator to being 8x to the 11th minus 4x to the 11th, all divided by x to the 8th. and then we can combine like terms and clean it up one more step with exponent properties, and we get 4x to the third, which we do know is the derivative of that. So that does work out. That does confirm that we have our derivative 4x to the third using the quotient rule. All right, so this one is on ours. I'm going to put these both up. On page 138, you can have the verbal description of the quotient rule. It takes the derivative of the quotient of two functions, take the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function, all over the bottom function squared. So that is how you would say it verbally. The book has it as well on page 138. We only use this formula when we can't divide and differentiate. So we try to save it when we have to use it. If there's a way to manipulate the equation at the beginning so we don't have to use the quotient rule, you can always try to do that as well. Example 1. Find the derivative given f of x equals x squared minus 1 divided by x squared plus 1. So we're going to apply this to the quotient rule. So it's going to be u prime v minus u v prime divided by v squared. Okay, so we're going to keep rewriting that and repracticing that down. One way to do this is to identify the top and bottom function as u and v, and then find their derivatives. These two both happen to have the same derivative of 2x. And then similar to how I taught the product rule, we can kind of cross multiply these pieces together. So we want u prime times v minus u times v prime on our numerator divided by the denominator squared. So it's going to look like this. I guess on my second part I wrote v prime times u, but it does work out the same. It helps for the distribution. So that's going to be our first step. Right here, the calculus is done. However, there's going to be many times where we want to know when the derivative equals 0, or we have to clean it up for a multiple choice problem, and some other things as we go through the year. So usually we won't leave it in this uncleaned up form. So what I'm going to do is take the 2x on the first piece and distribute it, and also on the second piece and distribute it. And it will clean up to 2x to the third plus 2x, and I'm going to leave the minus sign, although you could distribute it at the same time if you like. We get 2x to the third minus 2x. And then we can distribute the negative symbol, and we will have 4x left over on the numerator when we distribute this. The 2x to the thirds will cancel, one's positive, one negative, and then we get a negative and a negative, which is going to cause that to become positive. So we'll get 4x divided by x squared plus 1 quantity squared. So that will be our derivative. One thing we could do is take our graphing calculator and graph it to make sure that our function, the derivative we found, 4x divided by x squared plus 1 raised to the second, is actually going to be the same derivative, and then n deriv y sub 1, our function, with respect to x for all of x, and see that the y2 and y3 overlap. So you can do that with the graphing calculator to kind of verify that the derivative we found does work out. So that to verify our answer is reasonable. All right, example number 2, find the derivative given h of x equals a trigonometric function sine, so the fifth power of sine x divided by x to the third. I encourage you to pause the video and see if you can set up this quotient rule. One way, again, of organizing is to identify the top and bottom as u and v, and then find their derivatives. So we have the chain rule here, so we'll end up with 5 sine to the fourth power x times cosine. So if it does help you to write this as sine x raised to the fifth, that's fine. We have an inside and outside function that we need to find the derivative to. And then the denominator's derivative is pretty clean because it's a power rule. So now we have to take the derivative of the top function times the bottom, and then subtract it from the bottom function times the derivative of the bottom function times the top. So it's going to look something like this. So 5 sine to the fourth x times cosine x times the v function. So we have our u and our v. So this is u prime. This right here is v. And then this is going to be u right here and v prime, all divided by v squared. Okay, so just kind of getting your pieces and bearings with that. The order does matter because we are using subtraction and we're taking the difference of these two products. All right, so from here, the calculus is done, but we are going to go ahead and clean up some of the math. We have some things we can write out in front that are a little safer to write out in front, the x to the third and 3x squared. So I'm going to rearrange those to 5x to the third times the sine to the fourth power x, cosine x, and so forth. And then one of the things that we're going to notice is we have some common factors that can be cleaned up and reduced out, or the greatest common factored out. So if you notice, we have on the numerator an x to the third and an x squared, And also on the denominator, we have x to the 6th. Okay, so we have an x to the squared in all three positions that we can divide out and clean up. So when we do that, we can reduce all the x's by power of 2, and we're going to be with left x to the first, so 5x to the first, and then on the denominator, that 6 will be reduced down to a 4 as we cancel out these problems down. We're going to divide them all by, reduce them all by 2. Okay, so that is a very cleaned up version. There's a way you could factor out a sine value because you have sine to the 4th power, but that won't really clean it up too much. So this is our answer. I'm going to put a box around it because we are done. All right, example 3. Find the derivative given g of x equals 4x minus 1 quantity to the 7th power divided by 7x plus 2 quantity raised to the 4th power. So we have our top function and our bottom function, u and v, and then we're going to find their derivative. There is a chain rule involved, but the derivative of these inside functions happen to be constants, so they're not too bad. So we're going to get u prime is 7, so the derivative of the outside function with respect to the inside function is power rule. So 7 times 4x minus 1 quantity to now to the 6th power, and then that times by 4 is the derivative of the inside function. And then we repeat that on the second function. And then when we look at those, we really have 28, because we have 7 times 4 with that. So when we have that 28, we can put that out there on that. So we have really, this is 28 4x minus 1 to the 6th. So when we now have that, we're going to take u prime times v, which we have up on the numerator, minus u times v prime. Okay, so we have all those pieces. Now technically the calculus is done, but we have a lot of cleanup to do because we're going to want to clean this up to get it into nice clean factors in case we wanted to find out when the derivative equals 0, or if we were doing a multiple choice question, it would not be left in this kind of uncleaned up form. So what I'm going to do is I'm going to go ahead and write it where the 28s are out in front and kind of clean up those pieces, or at least part of the 28s. And then we're going to see that we have parts that are common factors. So we're going to work with cleaning up and factoring out some common factors. So I'm going to go to the next slide. Example 3, we're going to continue it. So this is our fraction. So we have 28s in 2 locations on the numerator. We also have 4x minus 1s raised to the 6th power and 7th, so we can factor out the lowest common value of that quantity to the 6th power. And then we also have 7x plus 2 to the 4th and 7x plus 2 to the 3rd, so we can factor out a 3rd power of those. So I'm going to go ahead and do that. So if you notice, I have brackets right here. The brackets just help my brain to say that that's what's left over. Okay, so I've taken out 6 of the 4x minus 1s, and this side had a 7, so there was 1 left over here. And then I took out 3 7x plus 2 quantities, so I was left with 1 left in the brackets. So now what I'm going to do is I'm going to collect like terms in the brackets. I have a 7x, and then I'm going to distribute that. I have a minus 4x and then a plus 1. So that's going to become 3x plus 3. And then from here, there's different ways to keep simplifying it. My next step is I see that I have a 3 in both of these factors. So I'm going to factor out a 3 and put it with the 28. So 28 times 3 is 84. And then what I'm going to look at is the fact that we have a common factor of 7x plus 2 on the numerator and 7x plus 2 on the denominator raised to the 3rd and the 8th. So it's kind of, we are going to simplify our exponents. And since there's a power of 8 on the denominator, when we subtract those, we're going to have 5 of those left on the denominator. So our final answer is 84, 4x minus 1 to the 6th quantity to the 6th power, x plus 1, all divided by 7x plus 2 quantity to the 5th. This is in factored form. If we wanted to know when this derivative g prime of x equaled 0 or was undefined, we'd be in a much better situation to do so. And put a box around it, we are done. All right, and here's an application problem of a population of 500 bacteria is introduced into a culture and grow in a number according to the equation P of t equals 500, parentheses 1 plus 4t divided by 50 plus t squared, where t is measured in hours. Find the rate at which the population is growing when t equals 2. So I'm going to take this formula, and all I've done in the first step is taken the 500. Because there's no exponent up here, I can distribute the 500 to the numerators and give 500 plus 2000t divided by 50 plus t squared. That's a little bit easier to handle because we are trying to find the rate, which means we need to find a derivative. And if we had left it in its original form, we would have a product rule and a quotient rule, which would not be very pretty to work with. So this is a little bit cleaned up. So now we're going to go ahead and take the derivative of P of t. I encourage you to pause the video and set that up on your own. All right, so p prime of t, the derivative of 500, this becomes 0. And then we have our quotient rule. So the derivative of the top function becomes 2,000 times the bottom function minus the top function, 2,000t, times the derivative of the bottom function, which will become just 2t, all divided by the bottom function squared. So you could kind of work with it from this point. I am going to clean it up. I'm going to take the 2,000 and distribute it, and the 2t and distribute it. So I'm going to get 100,000 plus 2,000 t squared minus 4,000 t squared. And those are like terms, so I can combine these two terms, and I should end up with 100,000 minus 2,000 t squared, all divided by 50 plus t squared quantity squared. So that is our p of t. And let's go back to the question, read what we're working with. Find the rate at which the population is growing at t equals 2. So at that moment in time of 2 hours, how fast is that population growing? So I need to find p prime of 2. So I'm going to substitute in 2. And when I do that, I get 2 squared because both positions have a t squared, so they're both going to become 4. That cleans up to 92,000 divided by 2,916. You could leave it like that as an improper fraction, or you can change it to a decimal. But before I do that, let's think about the units. So our input is in time, in hours, and our output is in bacteria. Okay, so since we're doing the derivative is where we divide the units. Okay, so several of us that started back in chapter 1 have gotten much better on it. So we need the change in y over the change in x for our derivatives because we're doing the values of the derivatives. So it's going to be the y value over the x value units. So we're going to get bacteria per hour. So 31.55 is the decimal, or you could leave it as the improper fraction. So at that moment in time, the population is increasing at a rate of 31.55 bacteria per hour. Okay, so since the positive derivative, we can know that it is an increasing population. So there's a word problem for us to kind of work out. All right, example number 6 is working with numeric form. Let y equal u divided by v be the quotient of the functions u and v. Find y prime of 2. And this one is numeric, where it's just giving you a lot of the ordered pairs. So again, we're working with a quotient rule states y prime would equal u prime times v minus u v prime divided by v squared. So we have to substitute those in. I'm going to go ahead and show one extra step of using it with the notation that y prime of 2 equals the following. You don't necessarily have to set that all up, but I do want to encourage you, you must show your calculus step. You will not get answers for just bald answers where you don't have any works to support them. So you do need to show that you are applying the quotient rule to some capacity with that. So u prime of 2 times v of 2 minus u of 2, v prime of 2, all divided by v of 2 quantity squared. So that's a good way to show that you're applying the quotient rule. And then we'll substitute into the proper pieces. So u prime of 2 is -4, and then so forth. We get 1 minus 3 times 2 as we substitute in those pieces of u of 2 and v prime of 2, all divided by v of 2 is 1, and then we quantity square. And so that will clean up to -4 minus 6, which is -10. So that is our derivative, y prime at 2. All right, so that's a numeric form. Our next one. Okay, for example 7, we're going to still do a numeric form, but which is a little different kind of formatting our function derivative notation. Suppose u and v are functions of x that are differentiable at x equals 0, and that u of 0 equals 5, and that next notation is du dx, so the derivative of u with respect to x at x equals 0 equals -3. So just some new notation. If you change your calculator into math print mode, you will start seeing this notation also on your calculator as well, with instead of n deriv. Find the value of the following derivative at x equals 0. So we're finding d dx of u divided by v. So I'm going to use this notation in the quotient rule just to show you how it would look. So du dx means the derivative of u with respect to x times v minus dv dx. I kind of guess I have that kind of little writ backwards. That's v prime times u. And that's still okay, but that is a little bit different notation than the order that we've been writing, divided by v squared. So then we have to substitute in those values. So d dx of u divided by v, we're taking the derivative, and that line, the vertical line has x equals 0, means we're taking the derivative at x equals 0. So that's the new notation of Leibniz that we're going to get more and more comfortable with. I know it's a little bit more writing, but there's more purpose behind it as we move forward. So now we're going to substitute in our values. So we get -3 and -1. minus 2 times 5, all divided by -1 quantity squared. So watch not to lose a negative symbol here. I have some students that end up with the answer of -13, but what happens is we get +3 minus 10, which will be -7. And then that is our numeric answer with that. And we are done. So that is a numeric example for our 7 examples of working with the quotient rule. So that's our quotient rule on that. The last little bit here, these 1, 2, and 3, I guess I would number them, but these questions right here are called excellent problems. They're on page 8 of our notes packet. They're also in the solution set of our homework guides in our haiku page. They are great problems to practice. In class, we did the first one, A and B, and then we did B from the second one, and we did C from the third one. So I do highly recommend practicing these problems and trying them out. Again, they're on our notes packet on page 8. Here are the answers only to these excellent questions after section 4.3. You will find the detailed solutions under the Solutions tab in Chapter 4 of our haiku page. I do highly recommend working out several of these problems and making sure that you understand the nice depth of them. And then we have our book homework as well. Please reach out if you have any questions. Thank you.